So just to recap whatever we have mentioned in the previous slides. So if we have two images, we will find the matching features like SIFT, for example, and we'll find like a translation transform. Okay, so this is what we found. We found these green arrows and we found red arrows. From our eyes, we know from the very beginning that this red eyes, of course, this is bad correspondence. Even if the SIFT feature told us that this point corresponding to this point and this point corresponding to this point, we know from our eyes that this is a bad correspondence. We know in advance that they are not a good match. However, for some reason, the SIFT or the descriptor at this particular location looks very similar to the descriptor of that particular other location. And the descriptor of this location looks very similar to the descriptor of this location, according to the algorithm. But what we need to do next is how we can have an algorithm that will be able to detect this bad correspondence automatically, not depending on our eyes. We need to have something that will catch that mistake automatically. How we can do that? If we were to work on something like that with the linear least square solution, I will get something on the average. So I will have all of these lines, assuming that all of them green as an example, and they say like, hey, the correct average correspondence will be something like that. And this will be my correct transformation. And according to this transformation, I will be able to transform any other point to any other point in the between the left image and the right image. However, this is not what we are planning to do. We need to get like something that will be able to catch things a little bit better. What we offered last time, something called ransack, but how many correspondence we need to compute a translation transform? If I know in advance that transferring from this to this happened only through translation. Let's say like something in the X, something in the Y, translation. How many correspondence do I need? I need two equations, and I can get two equations from just one point, which is one correspondence, correct? One point will be enough in order to know how the translation happened. So if I give you a point, and I give you another point, and I'm telling you that this is corresponding to that, you should be able to know just from this one point correspondence, the two equations, solve for the two unknowns, the shift in X and the shift in Y, correct? So we need just one. Okay, so one correspondence to find the translation model. Let's say we will pick that one correspondence. We are saying, as an example, that this is corresponding to that. We don't know, of course, that it is correct or right, assuming that we don't know that this is correct or right. Say like this is correspond to that. Okay, that should be fine. Then what we need to do is to count how many will be inliers and how many will be outliers. If you do this, you will find that this and this are considered two inliers. Do you remember like when we did points like that, and we said like this is the line and they have 2 points, and then we'll count all of the inliers like in something distance delta and something like that? You will do the same here, but just with the 2D. You will say like, yeah, this is as like same corresponding to that within some delta. And then we'll agree that both of these are inliers. And then you count the inliers, they are 2. Then go to the next one correspondence. Count how many inliers, 1, 2, 3, 4, 5 inliers. Then what you need to do is pick the model with the highest number of inliers. Then this means that actually we will neglect this correspondence. We'll say like, hey, this is not a correct correspondence, and we will go with this correspondence. So this will give us a better estimate of the transformation. So basically, ransack will get 4 points correspondence for this example, compute the H matrix using the data linear transform, and then count the inliers, and then keep H if largest number of inliers. So each time we calculate H, but we will keep the H with the highest number of inliers as we already mentioned. Just to go back, this will give me a certain H. H means transformation, correct? For this example, my H is just translation. However, we always mentioned, or we always like designed H for homography, which has 8 unknowns. for points. Yes. For this example, it's very simple. I said like I just need 1 point. But if I'm calculating for a bigger and bigger and bigger of unknowns, so this means that I will need more points correspondence and so on and so forth. And then keep the h is the largest number of inliers, and then recompute h using all of the inliers and so on and so forth. So in this feature matching, we are calculating the homography, which is the transformation matrix. Let's say like we'll call it T. Can be anything. T can be rotation, translation, homography, rigid, transform, simple transform, any transform that you will think of, but do this simultaneously using ransack. So I'll get H, but then I will use ransack in order like to avoid some of these H's, yes, in order like to get the correct H. So ransack is helping me to actually change a little bit or perturb a little bit my H to the correct possible H. So this is like the advantages and disadvantages of the ransack. So the advantage, simple and general, applicable to many different problems, and often works well in practice. But this is like sometimes like lots of parameters to tune. I need to choose the delta. I need to choose like how many of the points that I need to do like for correspondence and so on and so forth. Some time, as I showed you last time with the table, when I showed you like the percentage of E, percentage of the outliers, which is 1 minus E for the percentage of the inliers, and we have seen how E and S will affect my algorithm. So basically, if I have the number of outliers like very, very high, usually something like that will not work very well. But this is not a usual case in a typical application. Also, we can't always get like a good initialization of the model based on the minimum number of samples. So if I would like to pick a line, the minimum number of samples is 2. But if any other thing, if I have my model as a circle, or if I have my model as any other thing, sometimes it's difficult to pick like the smallest number of points in order to draw that particular model in some cases. However, ransack is used a lot, and it's very, very recommended in such particular application. So now we are switching the gear to another new stuff, which is geometric camera models, pure computer vision. Let's say that we have a sensor like that. This is my digital sensor. I have CCD or CMOS, whatever the thing is. At the end here, I have the sensors. Okay, that should be fine. And here, I have my real world object. I have this tree. So what would an image taken like this look like in the sensor? So I have this point corresponding to the others. Let's say like this particular point, like we have like a point source. Of course, this point source is just like direct all of the light to the sensors, correct? To all of the sensors. So it will be received by all of the sensors. The same happened if I pick this point. The same will happen with also that particular point that I am sending all of the points to all of the sensors. But also, by the way, this will happen here and here and here and here with all of these kind of rays. Okay. How do you think it will appear here? What does exactly the image on the sensor looks like? If I have something like that, this is transferred like this is transferred like this. Unfortunately, what I would find is something like that. All same points contribute to all sensor points. Very blurry. How we can solve something like that, or how usually at the very beginning, when they discovered the camera, what was the idea that they had in order like to have a good image? Oh, then they said that we have to put like a barrier here between the object and my sensors. In this object, in this barrier, we will have what we call a pinhole or an aperture. This is pinhole, we'll call an aperture. In this case, how the image will look like. So we have all of these rays, but a lot of these already blocked. We have the same with these, a lot of these already blocked. I have only this and this, correct? Then how the image will look basically on the sensor in that particular case, if I have this pinhole with this small aperture. How do you think the picture will appear now? It's like that. just like the same picture, but just flipped. Correct? And this is a lot better than just like without this particular pinhole ID. So this is just a copy of the real world object, but unfortunately inverted, and it may be scaled. We'll see now how. So this is like the pinhole camera, and this was the idea a while ago that if I have an object, I will have like this pinhole. When I do this, I will get the object flipped or inverted and scaled. Okay. So this is the case. We said that this is the pinhole aperture, and we'll have like what we call this sensor. We will have like an expressions now that we will stick on it from now on. This is called my image plane. And please concentrate, because from now on, I will use these expressions. This is called the image plane. This is called the pinhole. I will call it as the camera center of projection. So this is center of projection, which I know that this is the center of my camera, the center of projection of my camera. I will call this pinhole the center of projection. Okay, so I have an image plane. I have my center of projection. I have also this called focal length, F. This distance between my center of projection and my image plane, the focal length, F. What do you think will happen if I change this focal length to half F, to half its distance? What do you think the image will look like at that particular case? So again, with the idea of the ray, it will intersect with this in a smaller particular area, which will give me also the object inverted, but then half of the size. Correct? So if it wasn't the F with this size, if I have it in half F, it will be scaled with the half of the size. Okay, so sounds good. So of course, ideal pinhole has like very, very, very small size, but this is not always the case. What happens if we play a little bit with the size of the pinhole? So now the F is as it was, but I'm playing now with the size of my aperture of the pinhole. How do you think the image will look like? Try something like that. Will it appear like this? But I have more rays right now, correct? More rays means blurring. Yes, so now I have it a little bit blurred. So if you begin like to design something like that, and then you begin to play with the aperture size, you can try until you get like the best image in that particular focal length. So there is no guarantee that if I will go more, this means that it is blurred, and if I will go smaller and smaller, it will be okay. Because if you, for instance, agree that this is the best size, does it guarantee that if I will go more smaller, that it will be even better? Not always. It actually will go also the other way around, that it will have also a blurring image. But why? So if it is like more smaller, I have like the ray is a little bit smaller, so I'm expecting that it will be a more sharper image. Yes, this is what will happen until I will arrive to an optimum case. After that, unfortunately, it will go the other way around. But why? Because of diffraction. At a certain particular point, the diffraction will take more effect than the real particular rays. So what will happen if I have 2x pinhole diameter? So my pinhole diameter goes 2x, so I have 4x light. More light will go on through that particular hole. What will happen if I have 2x focal length? I even went further, yes? Went further, the light will be inversely proportional to that. Yes, I'm going further and further. So the light will be less and less. So it will be 1/4 of that particular light. Assuming now that I don't have the pinhole and I have a lens camera, how things will work. So lenses will map bundles of rays from points on the scene to the sensors. How this will exactly work? It works like very similar to the pinhole in some sense, as we will see right now. The pinhole is like that. The rays with this is this. The rays with this is this. But with this pinhole, I have this image. What do you think the lens camera will do? Or how I can map the lens camera to the pinhole? If you look closely, we match it only in these particular lines. So this is in the pinhole, but this is also here in the lens, yes? Both of them are exactly the same in that particular only lines, but other than that, they are not the same. So central rays propagates in the same way for both models. Okay. So again, just to remind you, the focal length is between the aperture and the sensor. Aperture is the pinhole. It's called aperture. But what is the focal length if I'm using a lens like that? What would be the focal length if I'm using, or what would be my f if I'm using a lens? Interestingly, the focal length of my particular lens here is a little bit defined differently. Basically, my focal length f of my lens will be the intersection of parallel rays. So if I have a ray here, if I have a ray here, these parallel rays at the end will be intersect at a certain particular focal point. And this focal point, the distance between this and this is basically my f. So the definition of f in the pinhole camera, it's not like the same f if I have a lens. All of these definitions, I'm expecting that you will be familiar with. So basically, we can derive properties and descriptions that hold for both camera if we use only central rays. I can say like this and this are approximately the same. We assume that the lens camera is in focus, meaning that this parallel line, if I have a parallel line here, it will intersect at the same focal, yes? So both of them has approximately the same focal, for instance, if I assume that. And of course, both of them will be at the same, and my camera will be in focus. Again, the focal length f will refer to different things for lens and for pinhole cameras, as we already explained. So now we would like to know what will be the transformation from my walled object to my camera, and from my camera to my image frame. So we need to know two transformations. One from the 3D object to the 2D camera, and then from this 2D camera to another 2D transform with the image itself, which we can think of this as image warping. We need to study all of these things. We need to know what will be the exact relation. So if I were to give you like a point in the space, and I'm asking you what is this point corresponding to the axis of your camera, what is the transformation? If I were to move a point from that 3D in the wall to my 3D camera position. And if I would take the image plane, what will be the relation between this image plane and the center of projection of the camera? We need to study all of these relations. We need to know how we can do the transformations. And this is what we will study. Let's assume right now that my 2D image point, or my camera 2D image point, will be transferred from my 3D walled point by a certain particular matrix called P. So this is, in my 2D image, I have only two axes, X and Y. But in my 3D image, I have three axes, X and Y and Z. So this is X will equal to P, and this will be equal to X. But we would like to write this in the homogeneous domain. Do you remember when we went from the non-homogeneous to the homogeneous, we add like another one here? Let's say like we have here the Z, but with the 3D, we will add also the one here. So now I have the 4 stuff instead of the 3. And accordingly, this P needs to be like 3 multiplied by 4 in order to match exactly my homogeneous domain right now, or my homogeneous world coordinate. So I have P1, P2, all the way till P12. What we need to do, or what we need to calculate, is this P. I have this dimension, and I would like to see how this will be transferred to this particular dimension. So again, this is my camera center, this is my focal length, and this is my image plane. This is my image plane. What will happen if I move my image plane in the other direction? Again, this is my center of projection, so this is my camera. Yes, or center of projection of the camera. My image plane usually like back, so I will get my image inverted. What do you think will happen if I move my image plane here? The image will be exactly with the same exact scale, but it's not inverted. Yes, it is correct. But why I need to do that? It's just mathematically, as you will see, more convenient. But we know in advance that it is in the other way around. However, we will just move to do the math easily. Okay? So the image plane now moved from here to this particular place, and this is again my center of projection. We need to get a relation between the 3D here and my center of projection. And we'll also need to get like a relation between my image plane itself and the camera, as we will see shortly. So here I have my X in my wall. This is my center of projection. I have my point X in my image plane like that. First, I would like to highlight that this is my center of projection. This is my camera center. In addition, this axis is called the principal axis. So this Z axis is the principal axis. As you can see, here is the Y, here is the Z, here is the X. It just follows the right hand rule. Also, this image plane is F away from my center of projection. So the Z in this direction is equal to F. So it is away by F. And this is, by the way, is what we already mentioned here. This is away from my center of projection by F. Yes, so I'm just trying to represent the pinhole camera exact idea. So what is the equation for image coordinate X in terms of X? I need to get this image coordinate according to that X. How we can do that? It is simple. So let's say that I will have this triangle, and I have also this triangle. It's an easy match, correct? So I can get now some of the data that I need. So this is my triangle. This is my other triangle. And I would like to get, as an example, this. And also I would like to get this. How I can do that? Simple geometry. I think you have covered something like that in the high school. You can do that this distance over this distance is equal to this distance over this distance. Or the other way around. This is over this is equal to this over this. So this is equal to y f divided by z. Correct? You can do the same, and you can get also that this is equal to x f over z. So now we have a relation. Now we can relate this particular point dimension to this particular point dimension. If you would like to see this in the 3D case, this will be my image in the wall. This is my projection in my image frame. And I basically would like to calculate this y, given this y, and this x, given this x. It is the same as I just told you. X small will be equal to x multiplied by f over z. y small will be equal to y capital multiplied by f over z. And this is like the two triangles that I may take. I think in the 3D it looks a little bit better. You can see like all of the angles. Much easier. Okay, so now I have my x, y, and z. We can represent that in the other domain by f multiply x divided by z, f multiplied by y divide my z, given that I know this particular point. So again, just to remind you, small x is equal to p capital multiplied by x capital. This is our target, correct? But now I can easily get this because I already know the relation between this coordinate and this coordinate. How? We just mentioned that this x small equal to that. This is y small is equal to this. Correct? I can put this and this fx over z, fy over z, and then z, the homogeneous coordinate, correct? Correct? And then, I'm sorry. In the homogeneous coordinate, I will just put 1. Correct? After that, I can just multiply by z. If I multiply by z, this will go, and then I will have here a z, and this is what you have here. So this is not but my small x in my homogeneous domain, correct? So now I have this small x point as x. X here is not like the x direction. X means point x. Let's call it whatever the point name is, which has like an x and y and z. Its x is fx capital, its y is fy capital, and its z is just z in the homogeneous domain. It will be equal to p, because x small, as we mentioned, is equal to p, multiplied by x capital. This x capital in the homogeneous domain is x, y, and z and 1. This is point x, and that's why maybe put it like bold. And this is also bold. What is p? I think this is very easy to know what is p, because you already know what is the left-hand side, which is this fx, fy, z, and you know what is this. Let's multiply this by this to get this. How I do that? If I put here f, so f multiplied by x plus 0 multiplied by y plus 0 multiplied by z plus 0 multiplied by 1 will give me fx. Correct? Matrix multiplication, yes, I don't have to review matrix multiplication, correct? How about the other one? In order to get this one, again, this is my point x, this is my p, and this is my point x, bold x. How I can get this? If I put this is 0, and then I put this is f, 0, 0, 0 multiplied by x plus f multiplied by y plus this 0 and 0, I will get fy, which is this. Correct? How about the third one? How to get the z? 0, 0, 1. So 0, 0, 1, 0 will get me this. So now I know what is p. Okay. So now I know what is exactly p. I have the p, f, and 1. Correct? In some cases, in some other places, if you were to read, you may say, or you may find that this is, looks like that. This is 1 over f, zeros, and then 0, 1 over f, 0, 0, 0, but this what should be? F. Because basically multiplied by f or divided by f will not make any difference in the homogeneous coordinates. Something like that, just like in general, will not change the rank of the matrix. It will not give like homogeneous, just maybe scaled. But even with this homogeneous, since I will divide by this scale factor, so it will not make a lot of difference. So this is exactly the other one. But we prefer to write that way. So now the camera and the image, of course, have different coordinate system. I have my camera, I have my image, so it's not like the same exact center, correct? I have even this x in the world, and this is my point x, but this x is referred to this origin. It's not referred to this origin, because this is my image plane, but this is my camera coordinates. We need to get like to see how this will affect me. In another sense, this is my image coordinate, this is my camera coordinate. How I can transfer this to this, or the other way around. I have my point, I have P, correct? So now we got like that to that particular origin, but how we can go to the other origin? You can think of this simply as that guy's shift will be with a certain particular scale or whatever value to the x and with the other value to the y. But where this will affect me here in the matrix? Just to change these two values. It was 0, 0, but now with this px and py, shift vector transforming camera origin to image origin. Now I'm changing from the camera to my image origin by this shift. Okay, so now this is my P. Can we write this P in another form? So this P, as you can see here, which is just as the previous slide, 3 by 4. Can we write a little bit differently? We can write actually P like that. This matrix, 3 by 3, multiplied by this matrix. But what is this matrix and what is that matrix? Or physically on tuition, what does that matrix mean? And what does that other one mean? The left one is just a homogeneous transformation from 2D to 2D. But the right one is the homogeneous projection from the 3D to the 2D, assuming, of course, that I have the image plane at z equal to 1. So this P, now I can write it K, and then this is I, matrix I, and this is just column 0. And this will be equal P. So from now on, P is equal to K multiplied by my identity matrix and then the column 0. At this 3 by 3, this I is 3 by 3, and this 0 is 3 by 1. So it is the same matrix P, but I wrote it differently a little bit. So again, just like to remind you that we need to get the point in the wallet with that particular coordinate, and we need to map this to the camera and its center of projection, like that. How we can do something like this. So again, we already saw like how we can go from this to this. We need to take into consideration my wallet coordinate right now. And then how we can do the translation. So just to remind you, I have my wallet coordinate. I have my camera coordinate. And I would like to go from this to this. How I can do that? This is my point in the whole world. But I would like to refer that particular point to this particular center of projection. How we can do that? You might say that what I need to do is transfer this center to this center, correct? By translation, yes? Whatever in the X, whatever in the Y, whatever in the Z, I just moved by particular translation. So from that to that particular coordinate system. But when you do that, when you translate this X, W, and again, X is a point. It's not like an X direction. This X tilde is a point. X, W is a point. When I do this transformation in the X and Y and Z, right now, so I take this origin, moved at this in the X, whatever like this in the Z, and then this is in the Y. So now this is here. But when I do that, my point that I will find which refer to the new coordinate, does not match exactly or does not align exactly with the xw point. Now I have a new point called, let's say, like xc. However, I'm expecting that both of them should be aligned because I would like xw to be referred to the center of projection. But unfortunately, after I took xw and then do the translation minus c, and see this is like a certain particular translation in the x and in the y and in the z, they didn't align. Why? I might need something else in order to make them align. If you think about that, what you need is a rotation. So if you took a point, so let's say like this is my x and y and z, and this is my x and y and z. I have done like translation like this, translation like this. So x, y, and z in the wallet, and this is x, y, and z in the camera. I take like the translation here, translation here, translation here, it match. But then how about the rotation? Yes? Is this rotation, by the way, in one direction? Should I account a rotation from this to this in one direction? Is one direction will be enough? So now I'm telling you that you will take this xw, please, minus c, so you are doing the translation, and then multiplied by r is the rotation. But this r, if you would think about this r, is this a rotation only in one direction? Or should I account for many angles? And which each of them will have like a different value, or it might have a different value. The correct answer that you need to take actually 3 angles. Yes? So you have like, as an example, to move like this, yes? And then move like that, yeah? And to move like that, yeah? So this is like 3 angles that you can do. Correct? Or the other thing, like one around the, whatever, one of the axes, the other around the other axis, and this is the other axis, and so on and so forth, yes? So this, and then this. So if I take this 3 rotation and 3 translation to my account, then I should be able to make them match. Just like to highlight the R, in the X direction, I might have like an alpha. In the Y direction, I might have the beta. In the Z direction, I might have the gamma. And this will be the transformation in each of these directions. So when I do that in the heterogeneous coordinate, and by the way, I forget to mention that this tilde means that I am in the heterogeneous domain or non-homogeneous domain. But how we can write this transformation in a homogeneous coordinates? So again, I took my point, translate, and then after translate, I rotate. I got my xc, and I'm expecting that xc will match or will be aligned with xw. But how I can write something like that in the homogeneous coordinates? If you do like the math, you will find that you can write xc as a point, again, xc bold, tilde, not tilde, here is homogeneous, sorry. So as, let's remove that from xc as a point, which is xc, yc, zc1, will be equal to this particular matrix multiplied by this particular xw point in the homogeneous domain. If you do the math, you will find that they are very, very similar. You will put this r and then minus rc and then 0 and then 1. What is this r? It's just a rotation matrix, 3 by 3. What is this 0? This is basically 0, 0, 0, 1 multiplied by 3. How about this one? It is just 1. It is just one value. How about this minus r multiplied by 3? It is vector. You can write this as well in that particular domain if you were like to write this as a matrix form in the non-homogeneous domain. You can write it that way. In the homogeneous domain, you can write it that way. This is xw tilde 1. You can write this just like xw in the this is also homogeneous domain. This is also the homogeneous domain because of this one. So what I did here, I just like to remove this, sorry about that. This is x tilde 1, correct? When I add the 1, it it is just a homogeneous domain. So I just wrote it in another way. I just took all of these. I said like this is x tilde 1. I then took all of these. It is x. Yeah, so I should write, I guess, in order to be correct, I should write it like that way. X tilde C1. This will be also one in a homogeneous domain. We need to look also what is this and this looks like, but after we do like some small stuff. So now we already said that x small will equal to p multiplied by xc, and we already showed that p is equal to k multiplied by the I and the 0. We already showed that. So this is p, and this is my xc. But I just showed you in the previous slide that xc is equal to this matrix multiplied by xw. So how I can refer this to this? Because this is my idea. This is what I need. This is what I'm targeting. How I can do that? Just to plug this xc here. So meaning that this guy will be equal to this here. So my x will be equal to p multiplied by xc, as xc is not but this one. So now I have already did already two transformation. One from the wallet to the center of projection, and then the other one is from the center of projection of the camera to the image plane. So now I can go from the wallet to the image plane easily by these two multiplication, as we will see later on.